It's not here today. Okay, so right now it shows up as exam 1. I might rename it like something like exam 1 raw score, and then have another one that says like exam 1 curve. It'll be like a like I said, about a 2.5 point curve. We kind of get that average up to 75. So what I noted, and I'll also post kind of the forms of the exam as well as the answer keys. So, you know, if you can see how many you got wrong, each one you got wrong with 5 points. So how many points you got, you can figure out how many you got wrong. You can kind of go through the answer key, figure out what those problems were if you want to, and kind of identify what you did wrong for help you moving forward, as you're kind of, you know, progressing into new topics. I will. What was I going to say on that? I had a thought and I lost it. But yeah, I'll get those answer keys up so you can kind of go through and check those. What I noticed was a lot of people who did a lot of A's, and then there was a lot of kind of like C's and high D's. So there was kind of a missing B range. So you either really understood it or you kind of were missing, you know, a significant portion of it, kind of dropped down past that B range. So you didn't do as well as you want to on this one. You know, remember, they're weighted according to which exam is your best. Right now on Canvas, I can only lock it in one way for all of you. And so obviously we only have one exam. So it's treating it as though it's your best exam right now. So it's weighted heavily. So if you didn't do so well, it's going to look, you know, kind of affect your grade more, pulling it down. And for those of you who did do well, it's really going to kind of help pull your grade up, right? Essentially, it's a weighted mean, right? So that heavier weight, whatever your exam score is going to influence your grade in the class right now a little bit more. Okay? If you have specific questions, want to go over them, reach out to me. Feel free to stop by my office during office hours. We can go through or work through any of them that you want. Other than that, any questions from you related to kind of the exams, and those you came in late and kind of get them after class? Yeah.
You before going, you always prove the exams or only when that 75?
Usually, if it's just a little bit below 75, and it's not always the case. It's kind of just depends on the semester, like whether or not that's the case. Like I said, you guys were really, I mean, almost spot on. I guess I questioned not even curving it, but because it was a little bit below 75, like I said, I'll probably add 2.5 points when I get back to kind of looking at exactly what the average was. And I'll put an announcement exactly what that curve was, but just a little bit to kind of bump up that average of 75. Any other questions? Yeah, don't expect, so I never tell people that I even necessarily use a curve, because you shouldn't be expecting a curve on the exam, because if you're expecting a curve, but nobody else kind of thinks about it, you might be in a bad place, right? If everyone does well and you were expecting a curve, and then there isn't one, you know, so I wouldn't expect one going into this. I mentioned last class, I was going to put that Learn Smart up, just get that done before we start class on Friday. I've also put the next set of Connect questions. I believe it's 15 questions. Some of them, the first couple are about the uniform distribution, so you could start chipping away at a couple of problems. Obviously, we haven't gotten very far into it. I want to get it up there early so you can start working through it and not save it all towards the end, because probably after today, we'll see how far we get. But definitely by Friday, I'll post that next Excel assignment. And you can kind of start chipping away at that as well, so that you don't save it all till the end. Okay? Any other questions before we get started here today? Some of this housekeeping stuff out there. All right, so I mentioned last class that we were going to need that file that was on Canvas as well, which is that Z table for those standard normal tables. So we'll start using those today. And really where we start with is this guy named Gauss, right? He was kind of a Renaissance man, really, really smart, worked in all areas of mathematics and science. Came up with this discovery of the normal distribution along with another statistician. And this really kind of revolutionized how we kind of approach statistics. In fact, we will primarily be talking about, or at least be around the subject of the normal distribution from here to the end of the course. Now, we'll use it to do different things, but it'll always kind of be there in the background. So we'll make sure we get a really good understanding kind of today and Friday, kind of building those, getting those building blocks of understanding the normal distribution down. So a lot of the times, when we think about this normal distribution, sometimes you'll see it referred to as the Gaussian distribution, because this is the guy that came up with it. Another word you'll kind of see for it is the bell curve. So, I've probably drawn it already in this class because I know that we'll be seeing it a lot. All right, it's going to look something like this. We'll talk about why it has the shape it does in a little bit, but for now, getting a little anecdote about this guy who kind of discovered it, right? So when he was young, he was misbehaving, and this teacher says, I'll keep him preoccupied for a while, go over in the corner, add the numbers up from 1 to 100. Right? So she thinks it's going to take him a while. He comes back in a matter of seconds and has the correct answer. Right? So as a little child, he was able to kind of come up with this in his head. But if I were going to add up the numbers 1 to 100, so 1 plus 2 is 3, plus 3 is 6. Right, plus 4 is 10. I would have to kind of continue. Right, that can take you a while. Right, the thing I kind of mentioned last class, right? Maybe it wasn't this section, but right, in mathematics, there's never like necessarily one right way to do things. Right, so there's a lot of ways that are probably the easier way to do things, but there are several approaches. So here, instead of using the method I just explained, what's 1 plus 100? 101. Well, it's 2 plus 99. 101. It's 3 plus 98. 101. That continues until you get down to 50 plus 51. 101. You've got 50 pairs that add up to 101. So 50 times 101 is 5,050. So these are like, different ways of approaching the same problem. I could add the numbers, right? 1 plus 2 is 3, plus 3 is 6. It's going to take me a much longer time. And I'll get to the correct answer, right? But if I can recognize these little patterns, potentially, there's easier ways to do. So, I don't know, kind of a final anecdote. Maybe like, I don't know, bet somebody that you can't add the numbers up from 1 to 100, in a certain amount of time, and you have this method, right? It'd be relatively easy. And really, there's a formula where you can do that with any number starting with 1, going up to whatever number you want. This formula would always kind of give you what that sum would be. Now, we're not necessarily going to use that, so it's kind of a fun way, a story about this guy, to introduce this normal distribution. So, he came up with this normal distribution, and really, it's just a unique example of a continuous random variable. Okay? So the problem is, we already talked about with these continuous random variables, the probability of any one value is going to be what? Infinite number of possible values. So the probability of any one value was 0. Right? But we can find the probability over intervals. Think about it this way: like if I have this normal distribution, for now, believing that the mean, right, it looks kind of like it's going to be in the middle of this distribution here. What this is telling me is that if I look at intervals of the same size now, right, so unlike a uniform distribution, let's say I look at the probability I'm in between, I don't know, 49 and 50. And down here, the probability I'm in between 9 and 10. I notice the area in between those two values, but under the curve, it's going to be much greater for certain values than it will for others. Right? So we no longer have this uniform distribution. We have a normal distribution. We're seeing values around the mean. It's going to be way more likely for us to see those values, and less likely for us to see values further from the mean. So that's kind of the setup we have. Well, how do I get this curve? Well, just like any other random variable, we have a probability density function. Okay, so we see a lot of variables take on this normal distribution, right? Human height, rainfall, really a lot of biological kind of measures, right? Weight. I'll show you a couple examples today, like human performance typically follows, like in, when I say human performance, usually I think kind of athletics or something like that, but also academically, you look at like IQ tests, they tend to have a normal distribution. So what does that distribution look like? Something like this. Now, don't write this down. We're not going to use this. Right? I mean, we are, but we're going to cheat a little bit. Okay? So this is kind of the function that would give us this normal distribution. So what we would have to do in practice is use this function, which is kind of an interesting to at least look at a little bit because it has those two numbers that pop up a lot, kind of in nature, pi and the natural number e. Right? Then the rest of it is really just look at different x values of different outcomes for this x variable. And then everything else is just your mean and your variance. Okay? So the normal distribution will be kind of dictated by whatever its mean and variance are. We can have several normal distributions, right? Human height and rainfall are both normally distributed, right? The mean height in inches is much greater than the mean rainfall every year. So the means can be different, but they can still be a normal distribution. We can see different variances, and still have a normal distribution. So there's no like rule about exactly how high or how flat this normal distribution has to be. In fact, the only properties we really need for this to be normal distribution is that it follows this probability density function. Depending on the mean and the variance, the shape of it will look a little bit different. Other than the fact that we know, and sorry, here's some labels that we kind of already got those out of the way, the mean, the variance, and those two natural numbers. So what we know is going to end up being true about the normal distribution, no matter what the mean, what the variance is that it will always be symmetric. So if I think about something being symmetric, that means that if I could draw a line down the middle of this distribution, it would perfectly fold on top of itself. So what ends up being true is that the probability of seeing something this far away from the mean or above it, and the probability of seeing something that same distance below it would have to be the same, right? So it's a symmetric distribution, right? Which means the mean will actually end up being equal to the median. We go all the way back when we were talking about skew. We said a normally distributed variable, the mean, the relationship of the mean to the median, they're the same thing. And that's what the normal distribution is. So it's symmetric, which lets us know the mean is equal to the median. It's going to be defined by the mean and the variance, which we'll kind of break down here for you in just a second. I think that's all I wanted to say there. So if I have different normal distributions, but one of them has a higher mean, what's that going to do kind of graphically to that distribution? If it has a higher mean, that's just going to shift that distribution to the right. So when we're thinking about different normal distributions, you know, if the mean is lower, shifts to the left, if the mean is higher, we shift that normal distribution to the right, right? But where we would plot that distribution depends on the mean. So changes in the mean moves that normal distribution along the x-axis. I don't think that's too crazy. What happens if it has a higher variance, right? So let's say I have two distributions with the same mean, but one of them has a higher variance. So here's my first one. Let's say it's got, I don't know, here's the mean. Let's say the variance is 10. What would happen if instead I have the same, right, same mean, but my second distribution has a much higher variance? So if you remember going back, what does the variance tell us? It tells us that the data or the outcomes here are more spread out. Or another way of thinking about this, the variance measured the deviation from the mean. So what it's saying is the higher the variance, the more deviation we see from that mean, which means that values far from the mean, right? Values really far from the mean are going to be more likely, right? The probability of seeing those values is now higher when we have a higher variance. So these outcomes that are very far from the mean, much more likely for us to see, whereas values near the mean kind of less likely, right? Less likely for us to see values near the mean, more likely for us to see values further from the mean. If I'm going to kind of connect the dots there, right? We end up with, when we have a higher variance, that will flatten our distribution. Kind of reflecting the fact that it's more likely we see values further from the mean, less likely we see values coming near that. Any questions on that? So that difference in mean shifts our distribution. Difference in variance kind of flattens, or if it's a lower variance, it would kind of peak that distribution, right? Or make it taller. Thinking about that. So I've got kind of a visual here of that, just in the slides, right? Going from 5 to 20, we can see that as the variance goes up, the height of our distribution goes down, or we get a flatter distribution. So if I'm looking at this, right, what can I say about male height relative to female height here? In the relationship to the mean and the variance, I should from this picture be able to tell which, you know, which of these groups, I guess, is a higher mean, which one has a higher variance. So, which one would have the higher mean? I'm kind of looking at the middle point of this data, right? and here, and here. So it looks like men have a little bit higher than me. Now, the first part you said was correct, right? They also have a higher variance, right? Why do we know they have a higher variance? Because, see if we look at this, right? It's a shorter or flatter, or the point that it's at its height on the y-axis is lower. Right? All those things are really just different ways of saying the same thing. Right? So this tends to be kind of what we see play out in these normal distributions when it comes to gender, which is kind of, I don't know, interesting that even in different things, women have like higher means, but it tends to be that males have kind of always a higher variance in the distribution, even if we're looking at things like IQ and different biological markers. I don't know enough about science to know why that is. I just know that when you look at that those variables, that's what we tend to see. So we could really do that though with anything, right? We could break down any variable. Think about, maybe we look at kind of comparing countries' average heights or average weights or rainfall or temperature measures, because those all follow normal distributions. We can compare across countries and say which countries have a higher variance in their temperatures or lower variances in their rainfall, whatever we want to do. Okay, so that's kind of some traits, some qualities, just some talk around that normal distribution. But we're actually going to be able to use that normal distribution to figure out the probability I see certain values. So I might be interested in something like, if I'm choosing a person at random, what's the probability they're taller than, I don't know, 74 inches, right? Well, I can use the fact that that variable is normally distributed to find that probability. Use that probability density function, integrate between whatever values I'm interested in, except for we don't have to do the integration. Someone's already done it for us. We're gonna have to kind of work our way to be able to use that work that people have already done. So we know the area under this curve, if it's a or if it's a continuous random variable, has to be equal to 1. Right? So think about the area underneath this normal distribution curve going from the highest to lowest possible value. I know that area has to be equal to 1. Okay? But if I go out 1 standard deviation below, and 1 standard deviation above that mean, no matter what the mean and standard deviation of that normal distribution are, the probability I'm somewhere within 1 standard deviation above and 1 standard deviation below will always be, what, 68.3% here, if that variable follows a normal distribution. And I'll prove this to you, probably not today, but I definitely will on Friday. So for now, kind of take me at my word. Okay? You don't have to have like these values memorized, but it is kind of interesting. So we then start to go 2 standard deviations above and below. Whoops. We're already up to the probability we see something within 2 standard deviations above and below is up to 99 or 95%. And if we go 3 standard deviations, we're up to 99.7%. Right? Like I said, well, I'll prove this to you more in depth next class, but for now, I'm kind of taking it at my word. But notice this kind of makes sense. As I go out more and more standard deviations, I'm just including more and more possible values for this random variable to take on. So, if the probability I see something between 30 and 40 is 0.3, well, the probability I see something between 20 and 50, a wider range of values, has to be greater than 0.3. And then as I kind of continue to go further and further out, including more and more possible values for this X variable to be equal to, that probability starts approaching 1. Okay? So you kind of think about it here visually as I go further and further out, there's just less area kind of in my tail set. Questions on this? So this is kind of comes out of the fact that it's a normal distribution. We actually are going to write these normal distributions as here's this random variable X, this little like squiggle line here, which kind of means it's distributed normally within whatever mean and whatever variance. Usually those will be numbers like given to us. Now, we have a special case where I've got a standard normal distribution, and that's going to be where I've got some normal distribution where the mean is equal to 0 and the variance is equal to 1. That's what we're going to call our standard normal distribution. Is that my computer? Okay, good. I was going to say, I hope that's not starting now. So we've got a mean 0, variance of 1, which ends up, right? What's our standard deviation then? Standard deviation is the square root of the variance. So the square root of 1 is. So the standard normal distribution has this nice property, which is that the variance and the standard deviation are both equal to 1. It's the only case where that's going to, it's the only situation where that's going to be the case. So now if I think about it, if I saw a value of 1 here, how far away is 1 from the mean? Well, it would be 1 standard deviation away. How far away is 2 from the mean? Well, if the mean is 0, 2 would be 2 standard deviations. And we kind of go on and so on and go through different values like that. So the standard normal distribution makes it, our interpretation of these values a little bit easier. So the goal is going to be to use and exploit the standard normal distribution. Because we've got all these normally distributed variables, but we don't want to do the integration every single time. So if I can convert a regular normal distribution into a standard normal distribution, someone's already done all the integration for us. You can kind of imagine if we went back to that probability density function, plugging a 0 in for the mean and a variance of 1 simplifies that formula quite a bit, makes it a lot easier to integrate between certain values. So someone's already done all that integration for this standard normal distribution for us. So we have to then think about how do we convert our x variable, this normally distributed variable, into a standard normal distribution. That's our goal. That's what we're kind of where we're going. So what we're going to start doing is instead of calling the values from a standard normal distribution x, for a standard normal distribution, we're going to start calling these z values. And the z values really just tell me the number of standard deviations away we are from that mean of 0. Right? I kind of already alluded to it earlier, but if I had a z-score of 1, well, I know that if I have a standard normal distribution, my standard deviation is equal to 1. So the value of 1 would be 1 standard deviation away from me. And the value of 2 is 2 standard deviations, right? So this interpretation of our z value is really nice for us, right? We can kind of determine how many standard deviations away from the mean. So, what else do I want to say here? I mentioned this. So how do I convert my original variable x into these z-scores? So think about it this way. If I could take a value, let's say we'll do the rainfall, right? So let's say that I want to know what's the probability I get more than 2 inches of rain next month. Well, if I have some different components, if I can turn that into a z-score, and that value of 2 inches of rain ends up being a z-score of, I don't know, 1.3, what we're saying is that that value of 2 inches of rain, that was our original x variable. When I turn it into a z-score of 1.3, that means the value of 2 is 1.3 standard deviations away from whatever the mean rainfall was. So I'm going to take this x variable, transform it into a z-score, and that z-score tells me how far away that original x variable was from the mean. Let me go before we kind of move here. Let me do try to give you another visual of what I'm talking about here. So I'll explain the process by how we do this in just a second. But if I have some variable x, and I don't know, the mean is equal to 50, what I want to do is turn this into a standard normal distribution. So let's say I'm interested in the probability that I see 70 or greater. What I want to do is to be able to determine what that z-score is, or how many standard deviations away from the mean that 70 is. Okay? Let's assume that my standard deviation is 10. Then when I turn that value of 70 into a z-score, I end up with a z-score of what? Yeah, it's the number of standard deviations away from the mean I am. So I'm 20 away from the mean. So I have a z-score of 2. Now that I have this z-score, I can use that standard normal table that I kind of mentioned you should print out to find the probability I see a z-score of 2 or higher from a normally distributed variable. Any questions on that? I haven't explained There's an easier way. Here with these numbers, it's very easy to see that that value is 2 standard deviations away. But in practice, it's probably gonna be a little bit tougher, right? My standard deviations might be like 8.31. So what's a nice equation that we have to turn these into z-scores? Would be something like this, right? So we're gonna take that original x value we were interested in. Over there was what, 70? We're gonna subtract the mean. Our mean was 50, divide by the standard deviation, and sure enough, we get that same z-score too. Right? It's just over there, it was a little bit easier intuitively to think about how many standard deviations away the value of 70 was. Okay? So if I were to convert my x values using this formula, my z-scores will always have a mean of 0 and a variance of 1. So let's think about, go through a quick example here. So here's my original variable x, right? If I subtract the mean from each one of these values, well, first of all, what is the mean? So add these up, divide by 4, I get what? 20 over 4. The mean is equal to 5. So I subtract 5 from each one of these values. So 2 minus 5 is -3, 4 minus 5, -1, 6 minus 5 is 1, 8 minus 5, no, sorry, or that are negative sign, positive 1, right? And then positive. So all I did there was subtract that mean from each one of those values. When I now find the mean of this new variable, right? I add these up, divide by 4, well, -3 plus -1. -4 plus 1 is -3 plus 3 is 0, right? Now I can divide 0 by 4 still, but it's still going to be 0, right? So when I subtract the mean from this x value, my new my new variable would always have a new mean of 0. I we call that demeaning variable, where essentially all I'm doing is taking that original normal distribution and kind of standardizing the mean so that it shifts that normal distribution back to 0, or that mean of 0. If I then determine what the standard deviation is here, so I go through, right, subtract the mean from each one of these values, square them, and then add them all up. So 2 minus 5 is -3 squared, so that's 9. Deviation from the mean is -1 squared, that's 1. 1 squared is 1. 3 squared is 9. That's all my deviations squared added up. Divide by n. This would give me my variance. So here I end up with what? 20 over 4. I have a nice one where that variance is also 5. So I don't want the variance, I want the standard deviation. So the standard deviation is going to be the square root of 5. Then complete my z-scores. I'm going to take those values where I subtract the mean and then divide them by the standard deviation. So I end up with what? -3 over the square root of 5, -1 over the square root of 5, 1 over the square root of 5, and 3 over the square root of 5. If I then take the deviation of each one of these values from that mean of 0, square those deviations, add them all up, divide by the number of numbers I have, I'll be finding, before we're kind of finding the variance and the standard deviation for that x variable. Now I want to find the variance for that z value. So first z value minus the mean of 0 squared. So basically it would just be that value, right? That value minus 0 is still that value. So if I square that, and it would what? 9 over 5 plus 1 over 5 plus 1 over 5 plus 9 over 5. I'll square all of these. I add them all up. Divide by the number of numbers that I have. Do that up to 20. 20 over 5 is 4. 4 over 4 is 1. Just kind of a quick, easy example. Sometimes when I tell this to be true, don't necessarily know why. I mean, other than the fact that I'm in front of the class, why you would necessarily believe me if I don't give you any justification, right? But here's a really quick, easy way we can prove to ourselves with data that if I subtract the mean and divide by the standard deviation, right, my new variable, we're calling it this z variable, will always have a mean of 0 and a variance of 1. And you can play around with whatever numbers you want to. Maybe if we get to Excel today, I'll give you a little example if there's time or Friday. So now that we have this z-score, we now know how many standard deviations away that original value for X is from the mean. Excuse me. So if it's positive, it tells me I'm a certain number of standard deviations above the mean. If it's negative, it tells me I'm a certain number of standard deviations below the mean. And our mean, right, will always have a z-score of 0, right? If I'm converting the mean of my original X variable into a z-score, it'll always have a z-score of 0 because, well, if I subtracted the mean from the mean, right, my numerator would always be 0. So, I was kind of like this visual, where if we think about being a certain number of standard deviations away from the mean, this translates into these nice z-scores. So if I'm 3 standard deviations below the mean, that's a z-score of -3. If I'm 2 standard deviations above the mean, that's a z-score of 2. And just another kind of neat, I don't know, I think sometimes it helps to see this. But I think about why also mathematically that works. Let's say my X value is 1.5 standard deviations above the mean. So that in practice, we see a number here. But if that number I knew was 1.5 standard deviations, when I turn it into a z-score by subtracting the mean and dividing by that standard deviation, we'll notice that cancels, that cancels. So if I had a value that was 1.5 standard deviations above the mean, sure enough, I'd always end up with a z-score of 1.5. So we can always map these original values of X onto their z-scores. So what use are these z-scores going to be? Well, maybe I want to find the probability of them in between two values. So that standard normal table, and I'll pull it up in a second, is basically going to be a cumulative density function for that normal distribution. Okay? So whenever I look a value up in that standard normal distribution, it's going to tell me the probability of seeing that value or anything below it, right? Cumulative probability. So we had said in our last class, if I wanted to find the probability between two numbers, I could take the cumulative density function for the larger value and subtract the cumulative density function for that lower value. So it's a little bit hard to do the normal distribution, but if we can use a standard normal distribution, someone's already done the work for us. Okay? So let's say I have this value of negative 1.29. So I had some original value for X. I turned it into a z-score, which I know would be coming from a standard normal distribution. I could look up that z-score of negative 1.29, and that z table, or that standard normal table, will tell me the probability I see this value or anything below it, right? Anything to the left. So what does that table look like and how are we going to use it? So I know it's very small, which is why I mentioned it's probably, kind of here's moving out. Make sure you print it out or able to pull a version of it open because it's going to be hard for you guys to see. And I can zoom in, but then we lose like a ton of the table and I'm scrolling around and it's too hard to follow. So just having it in front of you is going to be very beneficial. So notice here, my row headings, right, are going to be the first decimal of whatever my z value I'm wanting to look up is. So here we had negative 1.29, right? So the first thing I'm going to look up is negative 1.2. So we go down right here, right? Negative 1.2. I then use the column headings up there to look up my second decimal place, or the kind of hundredths place, right? So in my hundredths place, I have a 9. So negative 1.2, and then go over to the 0.09 column. Right? So negative 1.2. It's almost like you're adding what's on the column. So negative 1.2, except for it's not adding since we're in negative values, but you get the idea, right? It's kind of you're putting on to the hundreds place. So negative 1.29, right? Using that column heading. And the probability I see negative 1.29 or anything below it, the table tells me is that 0.0985. That table will always give me that cumulative probability. And so we first look up kind of whatever's in our 10th place, then whatever's in the 100th place, go to where those two, go to where that row and column would intersect, and that's the probability we see that z-score or anything below it. Or said differently, the probability I see something 1.29 standard deviations below the mean or even further from the mean. Any questions on this before we keep moving? Okay, so I also have positive z-scores on like the flip side of that table. So one side has all the negative values, one side has all the positive values. So before we kind of go through this one, I want to see if we can get this. So remember this over here. What if I instead wanted probability that I see a z-score of 1.29 or anything below. So without using the table, just using what we had already done. On that here. So one trait we had with any normal distribution, especially the standard normal, is that it's symmetric, right? So the area to the left of negative 1.29, if I were to like fold this over on top of itself, the area to the left of negative 1.29 is going to be the same as the area to the right of positive 1.29. So we looked that up already over there. Is it 0.0985? So if I want the area to the left of that, it's simply 1 minus that, right? Because I know the area under the curve is 1. So we can exploit the fact that this is a symmetric distribution to kind of, once we look up one value, it might be easier to then already know the, different probabilities. Here, if I knew the probability it's less than or equal to negative 1.29, I automatically know the probability it's greater than a z-score of positive 1.29. And then I could use that to find the probability it's less than 1.29. But if I wanted to, I could also just look it up here, right? So I go positive 1.2 all the way over to that 0.09 column. And sure enough, I get 1 minus 0.0985, which is 0.9015. Okay. So kind of different ways of approaching it, right? I can use the table again, or I can use this knowledge of the symmetric distribution to find certain areas. What's going to be true about every z-score that's negative? So if I think about my mean here is 0, every negative z-score, when I look it up in the table, it's going to have a probability less than what value? Yeah. So we said the mean is equal to the median because it's symmetric. So the area to the left and the right of the mean will always be 0.5. So if this, it almost seems like this entire area is 0.5, and I only want to know a much smaller part of that, well, that probably has to be less than 0.5. In fact, as soon as I get a negative z-score, right, the area to the left of that z-score starts to get below 0.5, closer and closer to 0. If I think about positive z-scores, the area to the left of a positive z-score should always be greater than 0.5, right? Because here, as soon as I get a positive z-score, now the area to the left of it is going to be something that's greater than 0.5. Right? And sure enough, that plays out in these tables. Notice all these positive z-scores, all these probabilities are above 0.5. We go back to the negative z-scores. All these probabilities are less than 0.5. In fact, if we go to 0.00, we get exactly 0.5. Okay? So those tables kind of remind us of that as well. All right. So, any questions on that before we kind of keep moving here? Where are we on time? All right. So we kind of already talked about this. We'll see a lot of z values start to pop up because it's like kind of floating around benchmark values, right? This is really close to 0.9, 0.95, 0.99. So we'll start to see the same z-scores pop up quite a bit. Okay. We kind of already talked about this, right? I can use that complement rule to find that the table always gives me the area to the left of a certain value. So if I want the area to the right, I can't get it directly from the table, but I can look that z-score up in the table, find the area to the left, right, and then subtract from 1. Find the published area. That's not too bad. We already talked about it's symmetric, right? So we'll get out of here a little earlier today. So I'm going to start this up real quick. Trying to get you guys some points for being here today. Dun, dun. It does want to start up for me. Guess I have to restart it here. So let's say I had something like, what's the probability z is greater than or equal to negative 2.53? Okay. Now, if you don't have the table in front of you, you still should be able to probably come up with what this one should be. So if you draw this out, think about you want the probability that you see something greater than that z-score of 2.53. So you can probably just from drawing this out and thinking about what we're doing with the normal distribution, you should be able to determine which of these is the correct answer. Now, if you use the table, the z-table, then you definitely can find, a little bit easier. But even just knowing the principles, should be able to come up with what the correct answer here is on this one. Go to the 1:30 mark. And we'll kind of talk about this a little bit. All right, if you haven't gotten an answer in, take your best guess. I think I counted 33 or 34, so I'm going to close it out. All right, so what I could have done, if I had that z-table in front of me, right, is look up that negative 2.53. So negative, I can get this in the same thing here, negative 2.53. And it tells me that probability is 0.0057, right? But the problem is, if I think about what I'm doing, what I want is the probability it was greater than that z-score. So if I've got this z-score, negative 2.53, I want the probability of seeing that something greater. Right away, I know it has to be greater than what probability? 0.5, right? Because there's the right of the mean would be 0.5. And I think the only other two options up there that were greater than 0.5 were like 0.99 something and 0.5057 or something. Well, the probability of seeing a certain z-value or greater was really close to 0.5. That should mean I should see a value really close to that mean of 0, right? So in order for the area to the right of a z-score to be 0.5, I would have to see a z-score that's really, really close to that mean of 0. So some really small negative z-score, like negative 0.1 or something. Well, I've got negative 2.5, so I can guess the probability is probably going to be a little bit closer to 1, right, than it is to that 0.5. Okay? So if I only have those two options left, 0.99 and 0.50 something, I should choose that value of 0.99. All right, so I had one more thing in the slide. We won't kind of use it as an eye clicker, but you should know how to find it. We just looked up and found the probability that z is less than or equal to negative 2.53. I showed you that was 0.0057. That one should be a little bit easier than the one we're looking for. The probability was greater than that z-score. And then I think I had, just to kind of prove to you, had some data laying around. There's human height, right, from a huge survey data. You can kind of see it's pretty close to a nice normal distribution. Right? Nothing's perfect. This is pretty close. So make sure you get that Learn Smart done before we show up to class on Friday. We'll kind of continue to go through the normal distribution and probably do some Excel work on Friday as well. Okay. All right. Enjoy your day. I'll see you guys on Friday.